Greetings, I'm Thirapat Trikopskunsin.
And I'm Batharamon Damrom Kitikun.
Our group will present about time series data analytics and our data analytics technique support vector regression. For the brief overview, you'll see how our data is complex and also how we pre-process, and how we explore our data, which is a time series data and also a multimodal data. You will also see how we apply support vector regression technique to predict our data. And also, we compare it to linear regression, since it's one of the two simple technique, and LSTM, long short-term memory, because it's a well-known technique used for time series data analytics. Now, how is our data complex? Of course, it's a time series and streaming data. We collect our data from two different sources. First, a primary sources from a sensor attached to a kit breakboard, collecting PM value for every 10 minutes. And secondly, from secondary sources, we use Open Weather API for also 10 minutes. Now, multimodal data, of course, because we collect it from two different sources, Kitbright and API, and we somehow need to integrate and join it to make use of it. For example, our time series data, the primary might be 15, 25, 35. On the other hand, secondary data might be 38, 48, 58. So we need to join these. And for target attribute that we aim to predict is PM2.5, PM10, and AQI, Air Quality Index. Here is a brief schema. You can see since the time series, there's a timestamp for both primary and secondary data. Now for our exploration, you can see that sometimes our kit breakboard might not work well, or maybe it's a database issue or Wi-Fi connection issue. There might be some missing value that we have to pre-process it. And since it's a time series data, line graph is quite essential for visualize the trends. Here is some graphs, line charts, and here is a bar chart. Because this is not exactly a trend, but is an hour within a day from 0 to 23, so bar chart is acceptable. And a histogram here is a distribution. There's a lot of graphs here, so you can see it if you want to in the PDF file. And one of our objectives in our core project is to explore potential relationship between air quality and PM concentration with the weather condition. So we plot some graph to visualize and see the potential relationship between it, weather condition, and PM AQI, even the day of week, some correlation. Here, graphs. Now for the pre-processing part, we first, as I mentioned, that is a multimodal, so we have to merge somehow. Now how we merge it? We pin the timestamp. Let's say it's 9:15, 9:25, 9:35. We pin it to 9 o'clock. Then we group the data and average it in that hours. And we use mode for categorical value. Then we join. In this case, we auto join with by the bin timestamp. Now, that's it. Now we have got our main table that we will use for data analytics. For missing value handling, we replace a skipped record or missing record with an iterative imputer using random forest regressor for the estimator. And we replace it with mode for categorical value. Now for feature engineering, we have include a lag feature and lead feature since our data is time series. What is the lag features? Let's say PM255, 1 hour lag means it's the data 1 hour ago of PM2.5. So we include PM2.5, PM10, and AQI lag for 1, 3, 6, 12, 22, and 72 hours. You can see how we apply it in the right-hand side in the Python code. And we also, on the other hand, lead feature, which instead of 1 hour ago data, now is a next 1 hour data. And we also include time series features. For example, day of week, and we one hot encode it, and hours from 0 to 23. But hour is not a ratio, it's an interval, and it's also a cycle with 0 and 23 actually are 1 hour apart. So we decide to cyclical encode it using a sign function right here. And some additional vector features. For example, is rain, which is a binomial, and some heavy and hot encode the vector condition because it's a categorical value. So now let's move on to our main topic, our data analytics technique, support vector regression, or SVR. For demonstrate how it works, I think see the visualization will be more clearer. So first of all, how to construct the SVR model. In general, the SVR model have two main parameters, which is epsilon and c. The epsilon indicate the width of the tube. Now the tube is the area between two dot lines. And for the c value, it indicates how much the SVR model fits the support vectors or the data points. So if you higher your c, the model will be more fitter, then it's become more complex. On the other hand, if you lower your c, the model will become simpler. Now, after set and select the parameters, we have to find the support vectors. Now, what is the support vectors? First, we have to use the model, the old model, if I say. So in this case, let's have a linear regression line as the old model. So we have to calculate the distance between the data points and the model. In this case, is basically an error. And if the error is beyond the epsilon value, those those data points become support vectors. And those whose value is less than the epsilon, the error is less than epsilon, we don't have to calculate it. Now, we have to weight the support vectors after this. And in this case, it's quite hard. For me, it's impossible to do it by hands, so we leave it for computers to do this task for us. We have to find a weight for each support vectors to indicate how much the model will fit and go to that data points or support vectors. Now, after find the weight, we can construct and create the equation. In this case, is the red line, as you can see here. Now, after know how it works, let's see our implementation. As I mentioned, that the lead feature we will use for prediction. Here we have PM2.5, PM10, and AQI for lead 1 day and 3 days as our target features. And we only collect the data for like a month, so I don't think the data will be enough for predict to a week. So we only have 1 day and 3 day predictions. So how we implement it? First, we train and test, splitting our data set. Then we scale it using standardization. After that, we use the grid source CV, the cross validation, to select the best parameters for the model. After that, we use that parameters to construct our model. Then we fit and create the complete model, which use the whole dataset, not only the trained dataset. After we have the complete SVR model, we use it to forecast and do a prediction. For example, let's say if I want to predict 1 day, I use the data for the last 24 hours and apply the 1 day prediction model. Then the result will be the next 24 hours data. And that's it for our analytic technique and implementation.
So about the demo part, we have two ways of calling the predicted data. The first is to call function in the class SVR predictor class. The reason why we had to make a class is because we used it in another project, the DAQ project. So we call get 1 day prediction or get 3 day prediction, and it's gonna return the PM 2.5, the PM 10.0, and AQI. These are all predicted data alongside with the timestamp. If it's 1 day, then it's gonna return 1 day from today. And then if it's 3 day, it's gonna return the predicted 3 day from today. The second way to call it is to use a function, SVR predict function. We put the data set, we put SVR, and then we put the parameter that we want it to be predicted, and then we call it. And it's gonna return the predicted data alongside with the timestamp. Like you can see here, if it's lead 1, then it's gonna return the predicted data from 1 day from today. And if it's 3 day, then it's gonna return 3 day from today of AQI. Here is for PM 2.5, and this is for PM 10.0. Now, I'm going to show you how we used the SVR predictor in our application. Our application is Raindrop Dust, which is from the DAQ project. So, you can see here that we display and visualize the data that we have collected from the data set. This and this is the predictive part that we used, the SVR. So here you can see that we have a 1 day and 3 days forecasting for air quality, and we display the average, minimum, and maximum predicted data of each parameters, which is AQI, PM 2.5, and PM 10.0. We also display trends of each next day too, alongside with next 3 days and next 3 day predicted data. So this is how we used the SVR predictor in a real life application. For the evaluation, We have two performances. The first is the model performance, which is a construction of each model for each target feature, and evaluate them by calculating the error using MSE. The lower is the better. The second is the application performance, which is the prediction of each target feature that we waited a few days and see the results. And then we calculate the error using MSE. The lower is still the better. So the result for model performance for 1 day, you can see that the best model is SVR. And for 3 days, the best model is the linear regression. But for the application performance, for 1 day, the best model is from the LSTM model, with the exception of AQI, that the best is SVR. And for 3 days, the best model is SVR model, with the exception of AQI, that the best is LSTM. So the conclusion is that SVR works just fine because it has been the best model in many occasions. And this is the comparisons of each model with the real data for 1 day and 3 days. This is for PM 2.5. This is for PM 10.0. And this is for AQI. So about the application, there's many ways to apply the SVR predictor into the use, such as forecasting PM, AQI, and particle, or for an air quality recommendation, or for a public health policy, or even for a research and strategy planning. And as I've shown you before about our raindrop dust, that we really use the SVR predictor in this application too. These are the references that we used. Thank you.